Okay, we'll pick up here with question E. We have a piecewise graph here. It's got quite a lot of interruptions and holes in it. And we're asked to make some evaluations and do some analysis on this graph. The first part of the question, part 1, says what is f of negative 6? To determine that, we first of all notice that each of these grid lines is 2 units. 1, 2, 3, 4, 5. So odd numbers are on the half, on the midpoint hash. So f of negative 6, to determine that, we count backwards. Negative 1, negative 2, negative 3, negative 4, 5, 6, negative 6. Then we go up or down until we intersect the graph, and we intersect the graph about right here. Now, really, that probably isn't actually negative 2, but that's what I've indicated if negative 6 equals negative 2. Probably more like negative 1.8 or something like that, but close enough. And so I've said that f of negative 6 is negative 2. I don't think that the graph on the exam is that unclear. I think all points that you're looking for are pretty obvious and pretty clear. So number 2 asks, what is f of 0? Well, to determine f of 0, we go to the y-axis and find the y-intercept. And the function crosses the graph at positive 1, so function value at 0 is 1. Part 3 asks for what value of x? F of x is equal to 0. Well, that's asking for x-intercepts. Well, there's only one because these two are undefined. That's the reason for the open circle. And so right here is the only place where we have an x-intercept, and it looks like that's negative 1, 2, 3, 4, 5, 6, 7. So f of x equals 0 at x equals negative 7. Then we're asked, what is the function value at 2? What is f of 2? Well, to do that, we count 1, 2, and we see that we're tempted to say it's 0, but no. You go up to see that the first point where the function is actually defined is at a function value of 6. So f of 2, the function value at 2 is 6. Part 5 says, what is f of negative 1? Function value at negative 1. So we count back from the y-axis to negative 1, and we go down past the open circle to the filled-in circle, which happens to be at negative 6. So the value of the function at negative 1 is negative 6. Then part 6 asks the intervals over which the function is increasing and decreasing. Well, the function is increasing from negative 1 to negative 1/2, but I have parentheses there because these open circles say that the function is not quite defined at negative 1/2, and at negative 1 it's defined here, but it's neither increasing nor decreasing at either of these spots here. So it's increasing from negative 1 to negative 1/2. Then from negative 1/2 to 2, it's increasing. Now it isn't increasing just because it's defined here at 2. That doesn't mean that the function is increasing there. It just means it's defined at 2. So it's increasing from negative 1/2 to 2. So once again, we have the parentheses to indicate that those points are not actually included. We just go all the way up as close as we can possibly get, and even closer to those points. And finally, from x is 2 to 2, 4, 6 to x is 6, the function is increasing again. And because it's not actually increasing here, it's neither increasing nor decreasing, these are also open intervals. That's what you call it when you have the parentheses that say these points are not included. Now the function is decreasing on only one interval, and that's from negative infinity. We assume that this function goes on and on uninterrupted, and so it's decreasing from negative infinity to negative 1. Negative infinity to negative 1, the function is dropping or decreasing. Excuse me. Now, for question F, we are given 1, 0 for a cubic function. And so if we use our synthetic division, that means that we'll easily be able to, we'll come up with a quadratic that hopefully we could factor. In this case, that is what has happened. So we have negative 2 is a 0 of the function. So we put 3, negative 8, negative 33, and negative 10 in our synthetic division frame, and put the negative 2 right here. We drop the 3 straight down. Negative 2 times 3 is negative 6. Negative 8 then, and negative 6 is negative 14. Negative 2 times negative 14 is positive 28. Negative 33 and positive 28 is negative 5. And not surprisingly, negative 2 times negative 5 is positive 10, which when added to the negative 10 gives us 0. Yes, because we were told that this value is a 0 of this function. So these coefficients, the 3, the negative 14, and the negative 5, are the coefficients of the quadratic, which is 1 degree less than what we started with, which is what happens when we perform our synthetic division. So this quotient is 3x squared minus 14x minus 5, and we can easily factor that. Since 3x minus 5 is negative 15, added to positive 1 times x is negative 14. So you set the 3x plus 1 equal to 0 and the x minus 5 equal to 0, and you find that you have 2 more zeros at negative 1/3 and positive 5. So the function has zeros at negative 2, negative 1/3, and positive 5. Now, for our question Z, I believe this is the exact question we were asked on the practice for exam 2. So it should be familiar to us. I just used the same graph that I used before. We're asked to create a polynomial function with zeros at x equals negative 2, negative 1, 0, and 1. And I will confess that I had intended to leave the grid out. You should not assume that this is a square graph. It's not. But we're asked to leave the polynomial in factored form. So if we have a 0 at negative 2, that means we'll have a factor of x plus 2. And if we have a 0 at negative 1, that means we'll have a factor of x plus 1. And if we have a 0 at 0, that means we'll just have an x by itself raised to whatever power we choose. And if we have a 0 at 1, we will have a factor of x minus 1. Now we're asked to give different multiplicities to each of these zeros, 1, 2, 3, and something greater than 3. So I just put them in order here, 1, 2, 3, and 4, which is greater than 3. And when I drew the function, I just put the 0 here at negative 2, negative 1, 0, and 1. And I didn't worry too much about extreme accuracy. I just made sure that the graph did slice straight through here at negative 2, which is what would happen with a multiplicity of 1. And it bounced off at negative 1, which is what would happen for a multiplicity of 2. And then it curves through at 0, which again is what would happen at a multiplicity of 3. And then it bounces again at positive 1, corresponding to a multiplicity of 4. And we're asked to sketch, and that's what's I've done here. Question H asks us to identify some characteristics of a rational function. We are asked to determine the y-intercept, any x-intercepts, and any holes in part C, which is something I did not talk about in class, but which I will talk about here, and again in the in-class review on Tuesday. So, and also we are asked to identify asymptotes, vertical, horizontal, oblique, as may be the case. So, whenever you encounter a rational function, the first thing that you should do is see if you can factor the numerator and factor the denominator. Well, this numerator factors as 2x plus 1 times 3x minus 2, and the denominator factors as x plus 3 times 3x minus 2. Well, 3x minus 2 is a common factor, and so it cancels multiplicatively, leaving the reduced version of the function as this, 2x plus 1 over x plus 3. And that's the version of the function that we use to determine intercepts and asymptotes. So to determine the y-intercept, that's going to occur when x is 0, so I substitute a 0 in for x here and here. And that leaves, as you can see, 1 over 3, 1/3. And so the y-intercept then is x is 0, y is 1/3. Now, to determine the x-intercepts, those are the zeros of the function, and so I set the numerator equal to 0, 2x plus 1 equals 0, and I subtract 1 from both sides and divide by 2, so that means x equals negative 1/2 is the only x-intercept, so x is negative 1/2, y is 0 is the x-intercept. Now to locate the holes, you go back to that common factor and you set it equal to 0 and solve. Add 2 to both sides, divide by 3, and so x is equal to 2/3. And so the function is undefined at x is equal to 2/3, and so it has a hole there. It does not have a vertical asymptote because the function reduces. And this is expressed this way intentionally because there are certain applications wherein we have one specific value where a function is a rational function is not defined, but a vertical asymptote does not exist there. So that's how you locate what's called a hole. If you were graphing this, at that point you would put one of those open circles. You would draw an open circle at that point. Now, as far as the asymptotes go, the horizontal asymptote is going to be the coefficients, the leading coefficients of either version in this case. So 6 over 3 is 2, as is 2 over 1, that's 2. So we have a horizontal asymptote at 2. Now the vertical asymptote, since negative 3 makes this denominator 0, negative 3 is the vertical asymptote, so the function never crosses the graph at x equals negative 3.